However, premium facilities sort the pieces, reserving the largest, widest sections for products requiring aesthetic appeal, while using smaller pieces for coconut milk where appearance doesn't matter. After extraction, the meat undergoes brown skin removal. The testa, that thin brown layer clinging to the outer surface, contains tannins that can impart bitter flavors and off-colors to the final product. Some manufacturers leave it on for products marketed as unrefined or traditional, but most remove it to create the pure white coconut milk that modern consumers prefer. Brown skin removal can be accomplished through several methods. Mechanical abrasion uses rotating drums lined with abrasive surfaces that scrub away the testa as the coconut pieces tumble. Chemical peeling employs brief treatments with mild alkali solutions that loosen the brown skin, followed by water rinsing. Manual peeling by workers remains common in facilities emphasizing quality, though it's the most time-consuming approach. The cleaned white coconut meat is immediately transferred to cold storage at 4 to 6 degrees Celsius, or 39 to 43 degrees Fahrenheit. At these temperatures, enzymatic activity slows dramatically, preventing oxidation and rancidity. The meat can be held for up to 24 hours if necessary, though most factories process it immediately to maintain peak freshness. The transformation from solid coconut meat to liquid milk begins with grinding. This crucial stage determines the final product's texture, fat content, and flavor profile. Coconut milk production is essentially a mechanical extraction process. Grinding ruptures the meat's cellular structure, releasing the oil and water trapped inside, which emulsifies into the creamy liquid we know as coconut milk. The coconut meat pieces are fed into industrial grinders, massive machines equipped with rotating blades or hammers that pulverize the meat into fine particles. The most common type is a hammer mill, where rapidly spinning hammers strike the coconut meat thousands of times per minute, reducing it to a paste-like consistency. These mills can process 500 to 1,000 kilograms of coconut meat per hour, operating at rotor speeds of 1,500 to 3,000 revolutions per minute. Water is added during grinding at carefully calculated ratios. This is where the distinction between coconut cream, thick milk, and thin milk is determined. For coconut cream, the richest, most concentrated product, the ratio is approximately 1 part water to 2 parts grated coconut. For thick coconut milk, it's about 1:1. For thin coconut milk or coconut water milk blends, ratios can reach 3 or 4 parts water to 1 part coconut. The temperature must be carefully controlled during grinding. The friction generated by high-speed grinding can raise the mixture's temperature significantly, sometimes exceeding 45 to 50 degrees Celsius, or 113 to 122 degrees Fahrenheit. Excessive heat damages the delicate flavor compounds and can start cooking the proteins, altering the milk's taste and texture. To prevent this, grinding equipment includes cooling jackets or systems that circulate chilled water around the grinding chamber, maintaining optimal temperatures of 25 to 30 degrees Celsius, or 77 to 86 degrees Fahrenheit. After grinding, the mixture resembles a thick, white paste, ground coconut suspended in water. This isn't yet coconut milk in its final form. It requires extraction to separate the liquid from the solid fibrous material. This extraction occurs in specialized machines called screw presses or hydraulic presses. Screw presses work like giant versions of home citrus juicers. The ground coconut mixture is fed into a tapered barrel containing a large rotating screw. As the screw turns, it compresses the mixture, squeezing out the liquid while pushing the solid material toward the discharge end. The pressure gradually increases along the screw's length, with maximum pressures reaching 100 to 150 bar, or 1,450 to 2,175 pounds per square inch. The extracted coconut milk flows through perforated screens in the barrel walls, while the pressed fiber, called coconut cake or copper cake, exits as a dense, relatively dry mass. Hydraulic presses offer an alternative extraction method. The ground coconut mixture is loaded into filter cloths or bags, stacked in layers, and subjected to hydraulic pressure. Pressures can reach 200 to 300 bar, or 2,900 to 4,350 pounds per square inch, squeezing out every possible drop of milk. This method typically achieves higher extraction efficiency, 90 to 95% compared to 85 to 90% for screw presses, but operates in batches rather than continuously, limiting throughput. The extracted liquid is the first pressed coconut milk, also called coconut cream, when using minimal water. It's rich, thick, and intensely flavored. The remaining coconut cake still contains considerable amounts of trapped milk. Rather than waste this, most factories perform a second extraction. The cake is mixed with fresh water, typically at a 2 to 1 or 3 to 1 water to cake ratio, reground briefly and pressed again. The second pressed milk is thinner and less flavorful, but still valuable. Many manufacturers blend first and second pressed milk to achieve desired consistency and fat content while maximizing yield. The extracted coconut milk isn't uniform. It's a mixture of different fat globule sizes, proteins, and water. Without further processing, it would separate rapidly, with the fat rising to the top and forming a thick cream layer. While some traditional products embrace this separation, most modern coconut milk products aim for stable, homogeneous consistency throughout their shelf life. Homogenization solves this problem. The coconut milk is pumped through homogenizers, high-pressure devices that force the liquid through tiny orifices at pressures of 100 to 250 bar, or 1,450 to 3,625 pounds per square inch. This intense pressure shears the large fat globules, breaking them into microscopic particles, typically less than 1 micron in diameter. These tiny droplets remain suspended in the water phase rather than coalescing and separating. The homogenization process occurs in 2 stages. First stage homogenization breaks down the fat globules, while second stage homogenization at slightly lower pressure prevents them from immediately reclustering. The result is a smooth, creamy liquid with uniform consistency that won't separate even after months of storage. Standardization adjusts the milk's composition to meet specific product requirements. Different markets and applications demand different fat contents. Coconut cream contains 20 to 25% fat. Thick coconut milk has 15 to 18% fat, and light or reduced fat versions contain 5 to 7% fat. Manufacturers analyze each batch's fat content using rapid testing methods, then blend batches or add water to achieve target specifications. Additional ingredients may be added during standardization. Stabilizers like guar gum, xanthan gum, or carrageenan prevent fat separation and improve mouthfeel. These are typically used at concentrations of 0.1 to 0.3%. Emulsifiers such as lecithin or mono and diglycerides help maintain the fat-water emulsion stability. Sugar may be added for sweetened coconut milk products, while salt enhances flavor in savory varieties. The standardized coconut milk is transferred to holding tanks, where it's continuously stirred to maintain uniformity while awaiting the next processing stage. These tanks are jacketed with cooling systems maintaining temperatures of 4 to 8 degrees Celsius, or 39 to 46 degrees. Coconut milk, a symbol of tropical indulgence and versatility, has been a staple in cuisines across Asia, Africa, and the Pacific for thousands of years. Originating in the coconut groves of Southeast Asia and Polynesia, coconut milk's journey from brown, hairy fruit to the creamy ingredient in your curry is a testament to human ingenuity. Today, it's integral in everything from cooking and beverages to cosmetics and health products, contributing to a global industry worth over $2.5 billion and growing. So how is it made? If you're curious about the incredible transformation from tree nut to creamy beverage, hit that subscribe button and drop a comment below telling us what surprises you most about coconut products. The journey of coconut milk begins in vast coconut plantations, primarily located in tropical regions. The world's largest coconut producers are Indonesia, the Philippines, India, and Sri Lanka, collectively accounting for over 75% of global production. These countries process an estimated 62 billion coconuts annually, with approximately 15 to 20% destined for coconut milk production. Coconuts used for milk production are typically mature nuts, harvested 11 to 12 months after flowering. At this stage, the coconut meat is thick, firm, and rich in oil, ideal for extracting the creamy, flavorful milk that consumers desire. Each mature coconut weighs between 1.4 and 2 kilograms, or 3 to 4.4 pounds, with the white meat or kernel accounting for about 30 to 40% of the total weight. Harvesting methods vary by region. In some areas, trained climbers scale the 20 to 30 meter tall palms using rope loops and collect coconuts by hand. In more modern operations, mechanical lifts or pole-mounted cutting tools allow workers to harvest from ground level, improving safety and efficiency. Some large-scale operations even employ trained monkeys in certain Southeast Asian countries, though this practice is declining due to animal welfare concerns. Once harvested, coconuts are transported to processing facilities in large trucks or carts. Quality is paramount. Only coconuts free from cracks, mold, or pest damage are accepted. Factories processing premium coconut milk may reject 10 to 15% of incoming coconuts during initial inspection, ensuring only the finest raw materials enter production. The coconuts arrive at the factory still in their outer husk, though some suppliers pre-husk them at the plantation. The timing between harvest and processing is critical. Coconuts must be processed within 24 to 48 hours to maintain freshness and prevent the meat from spoiling or developing off flavors. At the factory, the first major operation is dehusking, removing the thick, fibrous outer husk that surrounds a hard inner shell. This husk, made of core fiber, can be 5 to 10 centimeters thick and is incredibly tough, evolved to protect the seed during its ocean journeys as coconuts disperse across tropical regions. Modern factories use mechanical dehusking machines consisting of a sharp, pointed spike mounted on a sturdy base. Workers impale each coconut onto the spike, then lever it against the point to split and tear away the husk. Skilled operators can dehusk 100 to 150 coconuts per hour. The removed core is collected and sold to manufacturers of doormats, brushes, rope, and growing medium for horticulture, ensuring zero waste from this initial stage. After dehusking, the hard-shell coconuts proceed to washing stations where they're cleaned with high-pressure water jets. This removes any remaining husk fibers, dirt, and surface contaminants that could compromise product quality. The washing water contains mild detergents and sometimes dilute chlorine solutions for sanitization, typically at concentrations of 50 to 100 parts per million. The cleaned coconuts then pass through a drying section where hot air blowers remove surface moisture. Dry shells are essential for the next stage, splitting, as wet shells are more slippery and difficult to handle safely. The drying process takes just 2 to 3 minutes at temperatures around 60 to 70 degrees Celsius or 140 to 158 degrees Fahrenheit. Quality inspectors examine the dried coconuts one final time, checking for any cracks or damage that might have been missed earlier. Even at this stage, damaged coconuts are diverted to lower-grade production lines or sold for different applications like desiccated coconut or coconut oil extraction. The hard coconut shell must now be split open to access the precious white meat inside. This shell is remarkably strong. It's evolved to withstand being dropped from heights of 30 meters or more without breaking. Breaking through requires significant force applied at precisely the right point. Manual splitting involves workers using specialized machetes or cleavers to strike the coconut along its natural fault lines. 3 eyes at one end where the shell is thinner. Experienced workers can locate the optimal striking point by feel and split a coconut with just 2 or 3 blows, processing 40 to 60 coconuts per minute. However, most modern factories employ automated splitting machines. These devices use pneumatic or hydraulic presses that apply 500 to 800 kilograms of force, or 1,100 to 1,760 pounds, to crack the shell cleanly. Sensors detect each coconut's position and adjust the strike point automatically. These machines can process 1,200 to 1,500 coconuts per hour with minimal human intervention. As the shells split, the coconut water inside, distinct from coconut milk, drains out. This clear, slightly sweet liquid is collected through drainage channels beneath the splitting station. Far from being waste, coconut water has become a valuable byproduct. It's filtered, pasteurized, and either bottled as a beverage or concentrated for use in other products. A single factory processing 100,000 coconuts daily can harvest 15,000 to 20,000 liters of coconut water. The split coconut halves, now drained of their water, proceed on conveyor belts to the meat extraction stage. The timing is carefully managed. Exposed coconut meat begins oxidizing within minutes, potentially causing discoloration. Moving quickly from splitting to extraction minimizes its oxidation and maintains a pure white color that consumers expect. Extracting the coconut meat from the shell is perhaps the most labor-intensive stage, though automation has made significant advances in recent years. The meat adheres firmly to the inside of the shell, held by a thin brown skin called the testa. Removing it intact requires both force and finesse. In traditional operations, workers use specialized curved knives to pry the meat away from the shell. This requires considerable skill, too little force, and the meat won't release. Too much, and it tears into unusable fragments. Expert workers develop a rhythm, extracting whole or half shells of meat in 10 to 15 seconds per coconut. Modern factories increasingly use automated extraction machines. These devices employ rotating blades or scrapers that follow the shell's curvature, shaving the meat away in large pieces. Some advanced systems use pneumatic punches that separate meat from shell using controlled impacts, achieving extraction rates of 80 to 100 coconuts per minute with minimal breakage. The extracted meat pieces vary in size from large half shells to smaller fragments. All are acceptable for coconut milk production, as they'll be ground anyway. Fahrenheit, slowing bacterial growth and preserving freshness. Raw coconut milk is highly perishable. It's an ideal environment for bacterial growth due to its nutrients-neutral pH and water content. Without thermal treatment, it would spoil within hours at room temperature. Pasteurization or sterilization destroys harmful microorganisms and extends shelf life from hours to months. The specific thermal treatment depends on the intended product type. Refrigerated coconut milk typically undergoes pasteurization, heating to temperatures that kill most pathogenic bacteria while preserving fresh flavor. Shelf-stable coconut milk requires sterilization, more intense heating that destroys all microorganisms, including heat-resistant spores, enabling room temperature storage for years. For pasteurization, the most common method is high-temperature short-time, or HTSD, processing. The coconut milk flows through plate heat exchangers where it's rapidly heated to 72 to 85 degrees Celsius, or 162 to 185 degrees Fahrenheit, held at that temperature for 15 to 30 seconds, then rapidly cooled back to 4 to 6 degrees Celsius, or 39 to 43 degrees Fahrenheit. This brief, intense heating kills pathogens like E. coli, salmonella, and listeria while minimizing flavor changes. The entire process from cold to cold again takes less than 5 minutes. The plate heat exchangers used are marvels of engineering. Thin stainless steel plates with corrugated surfaces are stacked together, creating narrow channels. Hot water or steam flows through alternating channels, while coconut milk flows through the others. The thin channels and large surface area enable extremely rapid heat transfer. The milk heats from 4 to 85 degrees Celsius in just 10 to 15 seconds as it passes through the heating section. For shelf-stable products, ultra-high temperature, or UHT, sterilization is employed. The coconut milk is heated to 135 to 150 degrees Celsius, or 275 to 302 degrees Fahrenheit, for just 2 to 4 seconds. These extreme temperatures would normally cause severe flavor damage and protein coagulation, but a brief exposure time, combined with rapid cooling, minimizes these effects. The result is commercially sterile coconut milk that can be stored at room temperature for 12 months or more without refrigeration. UHT processing uses either direct or indirect heating methods. Direct heating injects culinary steam directly into the coconut milk, instantly raising its temperature. The milk then passes through a vacuum chamber where the added water from the steam evaporates, restoring the original concentration. Indirect heating uses tubular heat exchangers where the milk flows through tubes surrounded by steam or superheated water, achieving the same temperatures without direct steam contact. After sterilization, the coconut milk passes through a homogenization valve one final time. The heat treatment can cause some fat globule coalescence, so this post-sterilization homogenization ensures the product remains stable throughout storage. The pressures used are typically lower than initial homogenization, 50 to 100 bar or 725 to 1,450 pounds per square inch, sufficient to maintain emulsion stability without overprocessing. The processed coconut milk now moves to filling lines where it's packaged into its final containers. The packaging format depends on the market and product positioning. Cans, cartons, bottles, or pouches each have distinct advantages and challenges. Canned coconut milk remains the most common format, especially in Asian markets and for culinary applications. The cans are typically made from tin plate, thin steel sheets coated with tin to prevent corrosion. Before filling, the cans are cleaned using automated can washers that spray them with hot water and sometimes steam to remove any dust or manufacturing residue. The filling process must occur under strictly controlled conditions. For UHT sterilized coconut milk, aseptic filling is essential. The product and packaging must be kept sterile, and they must be combined in a sterile environment to prevent recontamination. The filling room operates under positive air pressure with HEPA-filtered air to exclude airborne microorganisms. Automatic filling machines position each can under a filling head, which dispenses a precise volume of coconut milk, typically 400 milliliters, 13.5 fluid ounces, though volumes vary by market. The filling nozzles use volumetric or weight-based systems, ensuring accuracy within 1 to 2%. High-speed lines can fill 200 to 400 cans per minute. Those smaller operations may run at 50 to 100 cans per minute. Immediately after filling, the can proceeds to a seaming machine that attaches and seals the lids. This process is called double seaming. The lid's edge is mechanically folded and crimped around the can body's flange in 2 rolling operations, creating an airtight hermetic seal. The seaming process must be precisely controlled. Improper seams can leak or allow contamination. Quality control technicians regularly inspect seam dimensions using specialized gauges, measuring seam thickness, height, and tightness to ensure they meet specifications. For products that were only pasteurized rather than UHT sterilized, an additional step called retort processing follows sealing. The sealed cans are loaded into retorts, large pressure vessels resembling industrial pressure cookers. The cans are heated with steam under pressure to 116 to 121 degrees Celsius, or 241 to 250 degrees Fahrenheit, for 15 to 30 minutes. This achieves commercial sterility even though the milk wasn't UHT treated before canning. The advantage is that retort cans can be filled on simpler, less expensive equipment without aseptic precautions. Carton packaging has gained popularity for retail coconut milk, especially in Western markets. These aseptic cartons, similar to juice boxes or milk cartons, consist of multiple layers: paperboard for structure, polyethylene for waterproofing, and aluminum foil for oxygen barrier properties. The cartons arrive flat and are formed, filled, and sealed in a continuous process on specialized machines like Tetra Pak or SIG combo block systems. The filling process for cartons is fascinating. The packaging material, a continuous reel of laminated paper, is sterilized using hydrogen peroxide baths or UV light as it enters the machine. It's then formed into a tube. The coconut milk is pumped into this tube, and the tube is sealed and cut into individual cartons. This all happens in a sterile chamber, ensuring the product remains uncontaminated. These machines can produce 6,000 to 12,000 cartons per hour, making them extremely efficient for large-scale production. Plastic bottles offer another packaging option, particularly for coconut milk beverages and drinking coconut milk products. High-density polyethylene, or HDPE, bottles are formed using blow molding. Preheated plastic preforms are inflated inside molds, creating hollow bottles. After cooling and quality inspection, they're filled with coconut milk and sealed with threaded caps or snap-on lids. Plastic packaging is lighter and more shatterproof than glass or cans, but provides less oxygen barrier, requiring either refrigeration or preservatives to maintain shelf life. Flexible pouches represent an emerging packaging format, especially popular in Asia. These pouches use multi-layer laminated films combining plastics with aluminum layers for barrier properties. They use less packaging material than rigid containers, reducing costs and environmental impact. Pouch filling machines fill and seal in one continuous motion, achieving high speeds of 100 to 150 pouches per minute, even on mid-scale equipment. Quality control is continuous throughout coconut milk production, but final product testing provides the ultimate verification that the coconut milk meets safety, quality, and legal standards before it reaches consumers. Microbiological testing ensures the product is safe to consume. Samples from each production batch are incubated in growth media and monitored for bacterial colonies. For UHT and retort processed products, the absence of any microbial growth after incubation at 30 to 37 degrees Celsius for 7 to 14 days confirms commercial sterility. Even a single colony forming unit per milliliter would cause the entire batch to be rejected and discarded. Chemical analysis verifies compositional specifications. Fat content is measured using methods like the Babcock test, Gerber test, or more modern infrared spectroscopy. The target fat percentage must be within narrow tolerances, typically plus or minus 0.5% of the specification. Protein content, total solids, and moisture are similarly analyzed to ensure consistency across batches. pH testing confirms the product's acidity level, typically ranging from 5.8 to 6.8 for pure coconut milk. pH outside this range might indicate contamination or processing errors. Some manufacturers adjust pH using food-grade acids or bases to achieve optimal stability and flavor. Sensory evaluation involves trained tasters who assess the coconut milk's appearance, aroma, taste, and mouthfeel against established standards. They look for defects like off flavors from rancidity, cooked notes from overprocessing, or separation indicating emulsion failure. Coconut milk should have a clean, fresh coconut aroma, creamy white color, smooth texture, and naturally sweet, nutty flavor without bitterness or sour notes. Physical testing examines parameters like viscosity, which affects the coconut milk's pourability and cooking performance. Rotational viscometers measure the resistance to flow, typically targeting 50 to 500 centipoise, depending on whether it's light coconut milk or thick coconut cream. Separation testing involves storing samples at various temperatures and periodically checking for phase separation. Ideally, properly homogenized coconut milk shows no separation even after months of storage. Packaging integrity testing ensures the containers are properly sealed and will protect the product throughout distribution and storage. Cans undergo leak testing using vacuum chambers or dye penetration methods. A small percentage from each production run is tested destructively, open and examined for proper fill levels, headspace, and any contamination. Non-destructive tests include visual inspection for dents and seam analysis using specialized measuring equipment. Allergen and contamination testing has become increasingly important. While coconut is classified as a tree nut and must be labeled accordingly in many countries, manufacturers also test for cross-contamination from other allergens if they process multiple products. Heavy metals testing ensures compliance with regulations. Lead, cadmium, and arsenic levels must be below specified limits, typically measured in parts per billion. Nutritional analysis provides the data for packaging labels. Fat, protein, carbohydrate, fiber, vitamins, and minerals are quantified using various analytical methods. This data must be accurate as it's used for nutrition labels that consumers rely on for dietary decisions. Every batch receives a unique lot code printed on the packaging. This traceability system links the finished product back through every stage of production to the original coconuts. If quality issues emerge after distribution, this system enables rapid identification and recall of affected batches while confirming the safety of others. Modern coconut milk factories exemplify zero-waste processing, transforming every component of the coconut into valuable products. This sustainability not only reduces environmental impact, but also improves economic efficiency. The coconut cake or copper meal remaining after milk extraction contains significant residual oil and protein, typically 10 to 15% fat and 15 to 20% protein. Rather than discarding this material, it's processed into several products. Desiccated coconut is one application. The pressed cake is dried, ground to specific particle sizes, and sold for baking and confectionery applications. The texture might be coarser than virgin desiccated coconut made directly from fresh meat, but it's perfectly acceptable for many industrial applications. Animal feed represents another major use. Coconut meal is highly nutritious for livestock, particularly ruminants like cattle and goats. It's mixed with other feed ingredients or pelleted for easier handling and storage. The high fiber content aids digestion, while the residual oil provides energy. Millions of tons of coconut meal are produced globally each year. making it a significant commodity in agricultural markets. Coconut oil extraction from the pressed cake offers another revenue stream. The cake is further dried and subjected to solvent extraction using food-grade hexane or mechanical pressing with higher pressure equipment. This yields coconut oil that, while lower grade than virgin coconut oil, is valuable for industrial applications, cosmetics, or further refining into cooking oil. The coconut water drained during shell splitting is too valuable to waste. Premium coconut water is filtered through activated carbon to remove any color or off flavors, then pasteurized and bottled as a standalone beverage. The global coconut water market exceeded $4 billion in recent years, making this byproduct potentially more valuable than the main product. Lower-grade coconut water is concentrated through evaporation or reverse osmosis, creating coconut water concentrate used in beverages, sports drinks, or as a fermentation substrate for coconut vinegar production. The coconut shells become fuel for factory boilers. After splitting and meat extraction, the hard shells are collected, dried, and burned to generate steam for heating and sterilization processes. Coconut shells have high calorific value, approximately 5,000 kilocalories per kilogram, making them an excellent renewable energy source. Some facilities have partially or fully replaced fossil fuels with coconut shell combustion, reducing both costs and carbon footprints. Alternatively, coconut shells are converted into activated carbon through controlled pyrolysis. The shells are heated in low-oxygen environments to 600 to 900 degrees Celsius, driving off volatile compounds and leaving behind nearly pure carbon with highly porous structure. This activated carbon is used in water filtration, air purification, and industrial processes. It's particularly valued for its hardness and low ash content compared to activated carbons from coal or wood. The brown coconut skin or testa removed during processing contains tannins, antioxidants, and fiber. While often discarded in the past, progressive facilities now extract these compounds for use in nutraceuticals, animal feed supplements, or natural dye production. Even the wastewater from coconut processing isn't wasted. After screening and filtration to remove solid particles, it undergoes biological treatment in wastewater treatment plants where bacteria break down organic matter. The clarified water can be recycled for non-food applications like washing or cooling, while the biosolids can be composted and used as fertilizer. After filling and sealing, the containers must be labeled with product information, branding, and legally required details. Labeling methods depend on the packaging format. Cans typically receive paper labels that are glued onto the cylindrical surface using automated labeling machines. The cans rotate past glue applicators that coat the back of labels with adhesive. Then the labels are pressed onto the cans by rollers or brushes. High-speed labeling machines can apply 200 to 400 labels per minute with precision positioning. Some manufacturers use direct printing instead. Inkjet or screen printing systems that print information directly onto can surface, eliminating the need for separate labels. Cartons are usually pre-printed before they arrive at the factory, with all branding and information already applied to the packaging material. However, variable information like production dates, lot codes, and expiration dates is printed during filling using inkjet printers that apply codes as cartons pass through the filling line. Bottles may receive shrink sleeve labels, printed plastic films that are slipped over the bottles and shrunk tightly using heat tunnels, conforming to the container's shape. Alternatively, pressure-sensitive labels are applied similarly to can labels, or bottles can be directly printed. All packaging must display specific information required by food labeling regulations. This includes a product name, ingredients list in descending order by weight, net quantity, manufacturer details, nutritional information, allergen warnings, storage instructions, and best before or use by dates. Many countries require dual language labeling, and ingredient names must follow approved terminology. Barcodes or QR codes are printed on all packaging for inventory management and point-of-sale scanning. These encode product information that retailers and distributors use for tracking and pricing. After labeling, the containers are organized into shipping units. Cans are typically packed into corrugated cardboard boxes, often in configurations of 12, 24, or 48 cans per box depending on size. The boxes are printed with product information and handling instructions like keeping cool, dry place, or stack maximum 8 boxes high. Automated case packers arrange the containers into boxes at speeds matching the filling line for a 300 can per minute line. The packer organizes cans into boxes of 24 at a rate of 12.5 boxes per minute. The filled boxes proceed to case sealers that fold and tape the box flaps, creating secure, closed packages ready for palletizing. Palletizing involves stacking the boxes onto wooden or plastic pallets in patterns that maximize stability and cube utilization. Automated palletizers use robotic arms or layer-forming equipment to build pallets according to programmed patterns, typically stacking 5 to 10 layers high depending on box size and weight. Each completed pallet is wrapped in stretch film that holds the boxes together and provides some protection against dust and moisture during transport and storage. The finished pallets move to warehouse storage to await shipment. For refrigerated products, this means cold storage at 2 to 6 degrees Celsius or 36 to 43 degrees Fahrenheit. Shelf-stable products can be stored at ambient temperatures, though climate-controlled warehouses maintaining 15 to 25 degrees Celsius or 59 to 77 degrees Fahrenheit are preferred to prevent excessive heat that could degrade quality over time. Inventory management systems track every pallet, recording production dates, lot codes, and storage locations. This enables first-in, first-out rotation, ensuring older stock ships before newer production, minimizing the risk of products approaching their expiration dates while still in the warehouse. Distribution networks deliver coconut milk from factories to consumers worldwide. The logistics depend heavily on whether the product is shelf-stable or refrigerated. Shelf-stable UHT or retort-processed coconut milk enjoys significant logistical advantages. It can be shipped at ambient temperature in standard shipping containers, reducing cost and complexity compared to refrigerated distribution. Ocean freight moves most international coconut milk shipments. Containers loaded at factories in Southeast Asia travel by ship to ports in North America, Europe, and other regions, a journey taking 2 to 6 weeks depending on route and distance. From ports, the containers transfer to trucks or trains for inland distribution to regional warehouses and distribution centers. From there, smaller deliveries reach individual retailers. The entire journey from factory to store shelf might take 4 to 8 weeks for international shipments or just days for domestic distribution. Refrigerated coconut milk requires cold chain logistics, maintaining temperatures of 2 to 6 degrees Celsius throughout distribution. Refrigerated trucks or containers transport the product, and all storage facilities must have refrigeration capacity. This cold chain significantly increases costs. Refrigerated distribution typically costs 30 to 50% more than ambient temperature shipping, but is essential for products that weren't sterilized for shelf stability. Sustainability initiatives are increasingly important in coconut milk production. Many manufacturers have implemented comprehensive environmental programs addressing multiple aspects of their operations. Water conservation is a major focus. Coconut processing uses substantial water for washing, extraction, and cooling. Modern factories implement water recycling systems that treat and reuse water for non-food contact applications, reducing total water consumption by 40 to 60% compared to traditional single-use systems. Energy efficiency initiatives include using coconut shells as biofuel, recovering waste heat from pasteurization and sterilization processes, and installing LED lighting and high-efficiency motors. Some facilities have achieved carbon neutrality or even carbon negativity by generating more renewable energy than they consume from fossil fuels. Packaging sustainability is evolving. Manufacturers are exploring plant-based plastics, increasing recycled content in packaging materials, and developing more easily recyclable package designs. Some brands have introduced fully recyclable aluminum cans or biodegradable cartons to appeal to environmentally conscious consumers. Fair trade and ethical sourcing programs ensure coconut farmers receive fair prices and work under acceptable conditions. Certification programs like Fair Trade, Rainforest Alliance, and organic certifications verify that coconuts are produced sustainably with fair labor practices. The coconut milk industry exemplifies how traditional foods can scale to industrial production while maintaining quality, safety, and increasingly, environmental responsibility. From ancient coconut groves to modern factories processing thousands of nuts per hour, the journey of coconut milk represents the intersection of nature's bounty and human innovation. In conclusion, coconut milk manufacturing is a remarkable process blending traditional knowledge with cutting-edge technology. From selective harvesting and mechanical dehusking to precision grinding, pasteurization, and aseptic packaging, the journey of coconut milk exemplifies modern food science at its finest. Each can or carton represents a transformation of a simple tropical fruit through dozens of carefully controlled steps, delivering safe, nutritious, and delicious coconut milk to millions of consumers worldwide. With factories processing over 100,000 coconuts daily and the global industry continuing to expand, coconut milk production stands as a testament to how industrial efficiency and natural ingredients can combine to meet growing global demand while increasingly embracing sustainability and ethical practices. If you found this fascinating, don't forget to subscribe for more incredible food manufacturing processes, and drop a comment below telling us what food or beverage production you'd like us to explore next. Thanks for watching, and we'll see you in the next video.